Let us return to our previous example of rolling 2 standard dice. What is the probability of rolling a particular outcome? For example, a red 3 and a blue 5, or a red 2 and a blue 6. As you remember, our sample space consists of 36 possible outcomes. Since the dice are fair, the probability of each of these 36 outcomes is equal. You will as often roll the combination 5-3 as 2-6. The probability for each outcome must therefore be 1 in 36. We use capital P to denote a probability. How would you then find the probability of a given event? Let us look at the event that the sum of the outcomes of rolling 2 dice equals 8, and let's call this event E. That's easy, as you can see. There are 5 possible outcomes, which give 8 as a sum. We can then calculate the probability of E by dividing the number of possible outcomes in our event by the number of all possible outcomes in our sample space. In this case, the probability of E equals 5 in 36, and we denote it by P of E. By the same argumentation, we can already tell that the probability of the event omega, the whole sample space, is 1. While this seems trivial, it is the first of 2 important properties that let us define probability functions. Let us now also consider another event G, which is the event that the sum of the 2 dice is 10. Then what is the probability that E or G occurs? Well, we need the probability of the union of E and G. This is also an event, so we can solve this in the same way. By simply counting the number of outcomes in the union of E and G, we see that this equals the sum of the 2 individual probabilities of E and G. Here we use to our advantage that our 2 events do not share any common outcomes. Such sets are called disjoint. Their intersection is empty. The fact that for disjoint events we can compute the probability of their union by simply adding their individual probability is the second important property that defines a probability function. To summarize, we can now define probability functions based on these 2 very intuitive properties. We say a probability function P is a function that assigns a value P of A between 0 and 1 to each event A, such that the probability of the sample space omega equals 1, and the probability of the union of 2 disjoint events equals the sum of their probabilities. However, we need to be careful when considering unions. Recall our event F, that contains all outcomes where both dice are even. Can we now compute the probability that E, the event that the outcomes sum to 8, or F occurs by simply adding their respective probabilities? Clearly not. By adding them, we would count the outcomes twice for which both E and F occur. We should therefore subtract the number of outcomes that are contained in both E and F in order to compute our probability. In this way, we find the probability of 11 in 36 that E or F occurs. This property can be summarized as the sum rule. Given any 2 events A and B, we can compute the probability of their union by adding their individual probabilities minus the probability of their intersection. And what happens if you are interested in the probability of an event not occurring? When simply counting outcomes again, we see that the number of outcomes in the complement of E equals the number of possible outcomes in our sample space minus the number of outcomes in E. The probability of E not occurring is therefore simply 1 minus the probability of E. This result is called the complement rule. Notice that in the example so far, we have calculated probabilities of events by dividing the number of outcomes in the event by the number of all possible outcomes of the experiment. These are experiments in which we have a finite number of equally likely outcomes. We call them Laplace experiments. Computation of probability is pretty easy in these experiments, Just count how many outcomes belong to your event and divide this by the number of outcomes in the entire sample space. Of course, not all statistical experiments are Laplace experiments. For example, consider a 6-sided die where a weight has been inserted near the corner where the faces contain the numbers 4, 5 and 6 meet. This makes it less probable to throw these numbers. We may get the following probabilities. We can still apply the computation rules as we did before. For instance, the probability of throwing an even number is the sum of the probabilities of throwing 2, 4 and 6. After the exercises, we will consider a new kind of probability, the conditional probability. See you then.